Now here's a quick synopsis of a couple of videos that preceded, because you might not have time to watch everything, and you might need no more than just what we're doing here. And let's go ahead and zoom in a little bit, which lengthens the quick synopsis slightly, but hopefully not too much. Okay, so if we have dt, d big T, d little t equal negative 0.5 times big T minus big T sub r, that's our rule for calculating the rate of change of big T with respect to little t. And big T is interpreted as temperature, little t as temperature of the room. So we bring something out into the room at temperature T, and we set it down, and it cools off, assuming big T is higher than little t, okay? Some temperature higher than the temperature of the room. So if we're higher than the temperature of the room, well, the thing is going to cool off faster than it does when the temperature is closer to the temperature of the room. The closer the temperatures get, the more slowly the temperature is going to change. So let's assume that the room has a temperature of 20. So, that's now given. T sub r is the temperature of the room, and that's 20. And let's assume that this object initially has temperature of 70. Okay, so that initially we're 50 degrees above the temperature of the room. Okay, but in any case, knowing the temperature of the room is 20, we replace T sub r by 20, and here's our rule for calculating the rate of temperature change. So if the initial temperature is 70, we're going to use a time increment of 0.4. Now we don't know what the units of temperature happen to be. We don't know what the unit of time happens to be. We're going to assume, though, that T equals 0 when little t, which we interpret as time, is 0, when big T, which is the temperature of this object that's going to cool down, is 70. And we're going to see how the object might cool down. Now the average rate of change, okay, well, now that we have that, we have to recognize that this means the rate of change of big T with respect to little t. Now the step that we never want to skip is we write out what the average rate of change of big T with respect to little t means. It means change in big T divided by change in little t. You have to know the verbatim statement, or the verbatim definition of a rate of change. And that verbatim definition tells you that this is going to be change in big T divided by change in little t, delta big T divided by delta little t. Okay, now, if big T is 70 when little t is 0, well, what do we want to do? We want to predict the approximate change in big T when the new, and then the new values of big T and little t after our delta t increment, after our 0.4 time unit increment. How do we do that? Well, we first calculate the rate. And by rate, I mean the rate of change of big T with respect to little t. So we calculate the rate. D big T over d little t is what? It's negative 0.5 times big T minus 20. And big T is 70, so it's this. And we calculate then the rate is negative 25. Now that would be negative 25 units of big T per unit of little t. But we don't have those units, so we don't bother writing it that way, but we need to understand that. So, since the rate is the change in big T over the change in little t, the change in big T, which is what we're trying to find so we can find our new temperature, is going to be equal to the rate times little t, times change in little t. And there's the calculation. It's going to be negative 10. So the temperature is going to decrease by 10 temperature units. So to get our new value of T, we add our initial value, 70, to the change, negative 10, and we get 60, so there's our new temperature. Our new value of little t, well, little t was 0, and the little t increment is 0.4, so our little t is going to be 0 plus 0.4, or just 0.4. Okay, now, big T is 60, little t is 0.4. Let's analyze the next increment. Well, that's very easy. The rate we get in the same way we did before, but we're going to plug 60 in instead of 70, and we get a rate of negative 20. Okay, and then delta big T is that rate times our delta little t, which is going to be, well, easily calculated to be negative 8. So our new temperature is going to be our 60 plus our -8, which is 52. New time, we're going to add 0.4 seconds because that's our time increment. That's the increment we use to analyze what happens to the temperature. Okay? And we can summarize that in a table, and the table goes on to a few more calculations. But once we have our little t and our big T, we can easily calculate the rate because we have this rule. Hope you can see it. I'm probably right in front of it, but you've seen it. And then we calculate our change in T based on the rate and our time increment. We add the change in T to our T. We get our new T, and new big T, and we get our new little t by adding the increment to our time. And we take those two and we put them down here so that now this is the starting point for our next increment. We do the calculations. We find our new temperature, our new time. These are our new temperature, new time. We write them down here, and they're the starting point for the next 0.4 unit, 0.4 time unit increment, and so forth. And we go as far as we want. The graph of our results here shows our big T as 70, and our little t, well, we've got 0.4 here, we've got 1.6 here. And what's going to happen is the temperature is going to keep decreasing toward that 20-degree temperature. Okay? Now, the closer it gets to the 20-degree temperature, the more slowly it's going to change. And just like if we step halfway to the wall, step halfway again, we never get there. We're never actually going to get there. The graph is going to look something like this, and it's going to have an asymptote at t equals 20. It's going to get closer and closer to big T equals 20, but it's never going to quite get there. Now, theoretically. The other thing we can do with this graph, it would be instructive, and I'm going to recommend it, that you calculate the slopes of this graph, treating it as a trapezoidal approximation graph with these points. And the slopes will give you kind of an idea that's going to come full circle and reinforce what's going on with these sorts of models.